Let's say you have a loaf of bread that you need to store somewhere in your house. If you have a bread box, that's perfect. It's custom built to be the right size. You probably won't think to yourself, though, that you need a whole closet or room to store your loaf of bread. It would be overkill to have a dedicated bread room, right? Capacitors are storage solutions for energy in your electronic devices. Like that loaf of bread, there are many ways you can store that energy, and not all storage solutions are right for every situation. So when you're choosing a capacitor, how do you know which is just right, like a bread box, and which is overkill, like a room dedicated to a single loaf of bread? Here to talk about how to decide which electrolytic capacitor is the best storage solution for your design is AVX fellow Ron Demko. Ron, welcome to Tech Chats.
Hi, Kate. Thank you very much. It's good to be here.
All right, so let's get started. Let's start with the basic question. What are aluminum electrolytic capacitors?
Well, they're polarized bulk capacitors, and they're usually used in low frequency applications. It might be a DC to DC converter, it might be some sort of power conversion or lighting. But generally speaking, they're used where you need a large amount of capacitance, and the exact tolerance of the capacitance isn't exactly the top priority, just a large amount of cap needed.
Just very quickly, let's take a little bit of a side trip here to talk about another basic concept, polarization. So most EEs typically learn about polarized capacitors, maybe in the first lab class where they're accidentally putting them backwards and blowing them up. What causes a device to be polarized?
Well, at first I have to admit that I have blown up a few of them in my
Oh
in
no.
my days here too. So, and anyway, so you can see that the symbols for polarized electrolytics are on the page here, and really the dielectric itself is one that has a different resistance in two different directions. So you don't want to run these in any reverse bias. Now it's important to be careful. So you don't want to exceed the voltage rating, the DC voltage rating of the part, if you have AC superimposed on a DC signal. But you have to be very careful that the AC is not larger than the applied DC, because the negative peaks of AC could then put this device into a negative bias, and that's not what you want to do.
Well, let's take another moment to talk about another thing that you have here on our visual aid, wet versus solid. What can you tell us about electrolytes?
There's three different main electrolytics, and now with aluminum electrolytics, we've got the whole spectrum, right? AVX is known for tantalum electrolytics. We have wet and solid, but the aluminum electrolytic also has wet and solid. The wet devices essentially are some of them have some water content in them, plus some other things to make the electrolytic function. The solid devices essentially are a polymer. That's where a lot of the advances came in the technology of electrolytics.
Mhm.
And solid electrolytics allow a reduced ESR. Always lower ESR is usually better. That implies a higher amount of ripple current. So it's a very attractive thing. And
Mhm.
there's also increased reliability.
Oh, fantastic. Yeah, and you do have quite a few little bullet points here pointing out the benefits and characteristics, right? So let's pull some of those apart just a little bit. Can't help but notice generally stable. What do we mean by generally in this context?
Well, across frequency, the electrolytic will start showing some amount of its inductance. These are basically wound technologies where we have aluminum foils with a separator, and they're wound to increase the maximum area of the electrodes. So across frequency, you'll see that the value of these will change slightly. Now, also with temperature, that will change a small amount. Um, in fact, that's one of the advantages of the solid electrolyte system.
Mhm.
The At low temperatures, a wet electrolyte system has a change in its properties where capacitance will drop and the ESR will increase. Well, solids are stable across that, somewhat like a tantalum capacitor is. Another interesting thing between the tantalum and the aluminum electrolytic is the permittivity, the
Mhm.
K factor. The tantalum part has the ability to have more capacitance per unit volume. However, the electrolytic, the aluminum electrolytic, has a very large increase in its anode by etching that material system. So it comes back off of the disadvantage of a lower K factor with a very large increase in the surface area of the anode. That's how come it could compete with tantalum.
Oh, very cool. Yeah. And generally speaking, can you tell us about how common maybe these different types of electrode materials are at this point? I think you mentioned obviously tantalum is very familiar to those who have used AVX capacitors in the past. What's the general shift looking like? What direction are we moving?
Well, it's interesting there because tantalum has a lot of legs to continue its growth. Electrolytics are well known, right? The aluminum electrolytic is a general purpose, large RMS current, just a big old bulk cap. And I think that's maybe not doing it enough justice. There's low ESR versions and high temp versions, and they work fine. The tantalums tend to be used in higher performance, smaller size type applications, even high rel applications. And niobium oxide, pretty much the same. It has some amount of self-healing characteristics that are advantageous. But electrolytics are going to do well, whatever the technology is. I think aluminum electrolytics is a good addition to what we offer. And the reason for that is so much more interest is occurring on the efficiency of power conversion and energy efficiency, the use of LED lighting. That's where the aluminum electrolytics are really going to show some strength there.
That's fantastic. And you do have a note on this slide as well that all three that we have listed here also are commonly used in those low frequency applications. Can you help us envision what low frequency means here?
Sure. It could be well, general purpose power conversion is pretty straightforward, right? Buck or boost or things like that. They could be used in lighting. They could be used in bulk decoupling, maybe some audio blocking. But they're not going to be used in high frequency switcher power supplies. That's more the area where stacked ceramics come into play. But
Mhm.
still, there's a massive amount of applications that are low frequency in nature, and that's where the aluminum electrolytic is going to do very well. I think the other thing that we could say is that the voltage range goes up to 400 volts. So I think the aluminum electrolytic voltage range is quite wide relative to that of our existing electrolytics of tantalum and niobium oxide. Going from 6.3 to 400 volts really allows you to work across the whole spectrum of applications that are out there.
Now let's move on and talk specifically about surface mount technology for aluminum electrolytics. What can you tell us about this space in particular?
Well, we have three different families of surface mount aluminum electrolytics. And it's important to talk about the basics of them because they're actually quite different devices. Although they look the same, the physical appearance of them looks as that on the right hand side, right? It's an aluminum case. There's a back plate, termination, and there's a marking on it.
Mm-hmm.
Well, on the left hand side, though, you'll notice that there's three different colors of marking that are associated with each of these families. The wet electrolytic system is marked in black, and the conductive polymers in red, the hybrid polymers in blue.
Mm-hmm.
So all of those have very different characteristics. The wet is more the general purpose electrolytic, whereas the conductive polymer, you could say that almost that's an advancement that has occurred. It has a lower ESR, a longer life, but in penalty for that, there's a higher DC leakage. Now, that's not necessarily a bad thing. It
Mm-hmm.
might prohibit it from working in a battery powered application, but where you have a need for lowered ESR and improved ripple voltage, perhaps on a power converter, that's very applicable. And then the hybrid polymer actually takes the best of both worlds, or pretty much takes the best of both worlds. And what that offers is a lower ESR, an enhanced life, and a low DC leakage. So
Mm-hmm.
you could almost say that's the most advanced part.
And that's actually exactly what I was going to ask you about. Like, any of these relatively new technologies? Are these going to be familiar to our listeners, or are any of these sort of new and different that they are just learning about now? Do you think?
Well, I think most people are familiar with the wet electrolytics, the general
Mm-hmm.
purpose ones. That's, probably the lowest cost and the largest volume. But with time, the advances came about that we wanted lower ESR. And the reason for that is, or one of the reasons for that is that the ICs and our loads require much less ripple voltage. So to get much less ripple voltage, you want to have a lower ESR, and that's where conductive polymers are doing a good job. And the hybrid polymer, of course, takes the best of both of those types of devices. So the actual electrolyte is where a lot of the development has recently occurred in this bulk capacitor.
Yeah, and actually, that's something that we noticed on our side is it's important to note that even in very familiar components like capacitors, there are still advancements being made.
Yes, that's right. So it's this by choosing the right part, you could optimize the life of your circuit. You could optimize the efficiency and perhaps things like power conversion efficiency, some of the flicker that might be associated with DC lighting, and all of that. So it's really important to know the differences between the wet electrolytic, the conductive polymer, and the hybrid polymer.
Next up, you have a zoom in on the surface mount aluminum electrolytic in particular. What are we looking at here?
So one of the other advances that had to occur to make electrolytics compete in today's electronics is a higher quality aluminum foil. And the reason you need to start with a high quality aluminum foil is really for one of reliability. Um, to get the large surface area, remember on our first slide, we showed the K factor of the aluminum electrolytic being low relative to that of tantalum or niobium. So to get the capacitance value in an aluminum electrolytic, we have to etch that anode aluminum foil. And when you etch any type of material, you might expose some impurities, and those impurities might have a much different anodization and oxide thickness than a pure device. So, the other big advancement in electrolytics, aluminum electrolytics, is using a very high purity foil. That foil then goes through anodization, it goes through winding, and then there's an electrolyte fill, whether it be the wet or the polymer or the hybrid, and then some final assembly. You can see on the right-hand side, it's wound up almost like two pieces of aluminum foil and a paper
Hmm.
towel. It's not that simple, but
Right.
generally speaking, it's in simple forms. That's what we've got. We put a piece of tape on it. It's got leads, and then we seal it in a can.
Hmm.
So it's a relatively simple process, but by knowing how these parts are built, we get a little bit better understanding of some of the things that we have to worry about in using them.
Yeah, and not everyone necessarily does these types of cross section, goes into the detail that you're getting into in this tech chat necessarily, and it can really change the way you look at capacitors, right?
Right. Yeah, I mean, ESR is one of the big concerns that you should have. Also, the inductance of the part. The fact that we said it's a low inductance, well, we said it's a low frequency part.
Hmm.
The reasons it tends to be a low frequency part is the usable frequency response of the device, both due to the material system and its construction. Well, we've changed the material system quite significantly, going from a wet electrolyte to the conductive polymer solid or even the hybrid. So that gives us a little bit more frequency advantage. And now I think we're getting into the geometric advantages or the geometric impacts of inductance. Incidentally, too, these are available in many different case sizes. They could be as small as an 0606 or as big as, well, a whole lot bigger than that, I think up to a 16 by 16.
You just mentioned that difference between the wet, the polymer, and the hybrid, and this is a nice little cross section explaining sort of the physical differences of what we see between the devices. Can you help us zoom in on the most important features that are on the slide here?
The first three things is to realize that we're talking wet polymer and then the hybrid. So the cans all look the same, the bottom
Hmm.
all looks the same. Everything that's different is on the inside, something that you don't see. And the only way to realize what you're dealing with is to know the color coding from the outside of the anode. The black being the wet, the red being the polymer, and blue being the hybrid. You've got essentially an electrode with a dielectric, and then you've got the counter electrode being that electrolyte, whether it be wet based or the solid polymer or the hybrid. But the fact that there's so many different case sizes that are offered in each series, that's a big deal, and that's very helpful for the designers. We have up to 10 different case sizes in some of these different families, which is it's it's hugely important to the designer. What we're showing here are three columns. We're showing the wet, where the polymer, and then the hybrid. And underneath each one of those is this particular AVX series that falls underneath those characteristics. In a high level view, you could say the wets are general purpose. Those are low cost device. They're low DCL, so that's a low leakage device. They're a broad value range. They can go up to 400 volts and up to 6800 microfarads. So, they're a great general purpose device, but you should always wonder, does the reliability match your circuit? Well, in the consumer world, it probably matches and exceeds it. It might exceed it in a variety of other different sectors, and it's
Hmm.
also important to check ESR. So, for instance, on wets, they might be great for battery-based devices where just we need some bulk capacitance, etc. The polymers take it a step further. That's where we have reduced the ESR. A lower ESR allows us to have higher current through the device with less temperature rise. So we could basically say there's a higher ripple current ability of this part because everything is essentially operating cooler. And because the electrolyte has no ability to dry out, it has an enhanced life. So these are great for LED type applications, general purpose lighting, perhaps computers.
Hmm.
Um, there's a very broad offering there, maybe even commercial and some industrial. But generally speaking, you could say these are used in efficient power conversion. And then the hybrid devices, well, that has a tremendous ESR, very low leakage and high reliability, with associated higher costs and some limitations on the range in terms of cap and maybe temperature rating, things like that, or voltage
Hmm.
rating. But there you get long life, very efficient, very low DCL. So those are great for industrial and commercial type power supplies. Anywhere you have long-term reliability concerns, even 5G stations, base stations, things like that. Tremendous
Hmm.
devices. Now, the importance of this, though, is it shows us that we've got a whole series of devices that range from the consumer world to the high-end industrial and long-term base station type world.
All right, so what we're looking at here is AVX's offering of the series of aluminum electrolytic capacitors, correct?
Yes, that's right. And what this table shows is the three different series of parts. The black, the wet electrolyte are in, you can see the picture of the part. You've got that black band on the anode. You've got the little triangle AVX symbol on the right. So that's our part. The red is our conductive polymer, and the blue is, of course, the hybrid. And we show the electrolyte system there. So generally speaking, the importance of this, it shows you the fundamental capacitance range that you could have, the voltage rating, and the a relative comparison of the hours of that type of device. If we go to slide 8, what we're looking at is a specific dive into the ESR of the part, the RMS current, and then the DCL, the leakage. And the reason that's important is it shows you really the details and why the wet electrolyte is the general purpose device. RMS currents are reasonable, but they're not anywhere near that what you would find in the polymer device. In the polymer, there's quite a range of those. That's reasonable, and in the enhanced reliability and the hybrid types of devices, you see a very low ESR, great RMS current capability, and a very low DCL, which is outstanding and very much needed.
Can you walk us through what this handy table at the left-hand side for PCB designers, what should they be seeing when they look at this?
Sure. Well, what we wanted to do is come up with a simple table that you could compare the wet electrolyte, the polymer, and the hybrid in terms of applications. So if we go to the polymer, we right in the center top, we could say, okay, they're great for power conversion. The reason is because they have a low ESR. And likewise, the same with hybrid. If we go down two columns and look at the battery for hybrid, anything that's battery operated, well, we want the battery to last a long time.
Mm.
And to last a long time, we have to have very low loading on that battery. The fact that polymers have a higher DCL, the higher leakage than the other two technologies, well, that's a negative in that case. They can be used there, but it's not the optimum component. And wets or hybrids would be great for use in battery applications. If we go to the bottom, we could see wets are great for high vibration, the same with hybrids, whereas the polymer might not be as good in that type of scenario.
Mhm.
So I like this table because it gives you some of the fundamental characteristics. And also, we talk about low temp and high temp capability. Um, the fact that there's no plus, incidentally, under extended reliability under the wet doesn't mean it's not good there. We just wanted to show that the polymer and the hybrid are outstanding in those particular scenarios.
You've got an application example for us, which is fantastic. Want to walk us through it?
What we really want to show is that the aluminum electrolytics could be used as either the input capacitor or the output capacitors in a variety of different power conversion systems that are out there. So, regardless of the exact system that you're working on for power conversion, it's very likely that there will be an electrolytic in either the input, the output, or both. And there's a possibility that there's some ceramics or some tantalums as well for extended frequency response. But the fundamental part, the fundamental bulk part, might very well be the electrolytic on this type of power converter.
So you have on here input capacitor, output capacitor, important for both, reducing voltage ripple, supporting instantaneous power demands. What else are people looking for in these?
Well, size and reliability. So the fact
Mhm.
that there's so many different sizes, but depending upon the series, is a big deal, and they could almost improve their reliability or tune their reliability based upon the expectations of that end system that they're working on. What this slide shows us, though, based upon what we've previously talked about, is that matrix of the three different electrolytes and
Right.
the two series per electrolyte gives the designer a huge number of options. And then also within those individual series, there's somewhere between 5 and 10 different case sizes. So there's a tremendous options for all of the designers to get the optimal part for that circuit.
This has been such a pleasure. Thank you so much for all of this in depth information. There's so much more to the world of capacitors than I think a lot of people realize or give them credit for. So thank you so much for walking us through this, Ron.
Thank you, Kate, and get ready for even better things to come.
Oh, absolutely. We will be waiting and watching AVX. Thank you so much, Ron.